Okay, hello and welcome to today's video where I will walk you through this integration manual, which is called Wireless and Bus to LoRaWAN Converter using the Things stack. So I will first quickly go through the text of the integration manual, and I will quickly explain to you the setup which I have here on the table. So we have our ACRIOS converter. It is the NI-W-D2 variant of the device with a special firmware which allows both LoRaWAN and NB-IoT to be available on this hardware. In this case, however, we are only using LoRaWAN and wireless and bus in this integration manual. So we have our ACRIOS converter, which is connected over via a LoRaWAN gateway and a UDP Semtech protocol to the Things stack over LoRaWAN, of course. This is running on a virtual private server. It is the Things stack with internally MQTT broker, and on my PC I have a main.py Python script which is connected via MQTT to this MQTT broker, and there is a text output which tells me what's actually happening. What I will show you in this video is how you can use the application level protocol we have, which is also used in case of wireless and bus to narrowband IoT, and how you can use this protocol to configure your ACRIOS converter to read out the meters you want, and to actually execute the gathering process. Okay, so in case you don't have your own instance of the Things stack, I have included here also a little tutorial in tutorial how to set up the Things stack. We have created this nice repository with Docker Compose file, which should help you to set things up. Alternatively, you can use any publicly available the Things stack if you want. Just be careful if you use an instance which is not using spreading factor 12 for RX2 window, RX2 LoRaWAN window. Make sure you count with that. In my case, I'm using spreading factor 12 for RX2 window. Okay, so I will not really go through this part because I have prepared this beforehand, but I have followed my own instructions to test actually these steps. So in case you have your own LoRaWAN gateway, if you simply follow all these instructions, you should be fine. And I have also provisioned my main.py script like this. So you need to put here the IP address of the MQTT broker and the port, of course. And you need to set up the uplink and downlink topics so that you can receive and send frames. And here you need to set up a key, API key from the Things stack. And this is also how you get the API key. But now let's jump to the actual logic of the main.py. So what you will see, I'm going to share the serial console of the device, of this device, and serial and not serial but standard output of the main.py script. So you will see an interaction happening, and this is what will happen. So first the script will connect to the MQTT broker, then it will wait for a beacon message. I will make the beacon message happen quicker by pushing this button, which makes the device send the beacon message right away. Then the script will send to the device the configuration. Then the device will acknowledge back the configuration. Then we will send a list of IDs which should be read out or gathered, and the device will send us back just a checksum of all these values. This part, I called it end device configuration part, which it basically covers the configuration part of the communication which needs to happen between your backend or any script and the converter. Second is demonstration of two scanning processes. In ACRIOS, we distinguish between gathering and scanning. Scanning is to get the information about the ID of the end meter and its signal strength. That's the first part of the scanning. That's the command 04 hexadecimal. And then there is also another command for scanning, which is 0f or 15, and we call it a payload scan request. And it basically means that it sends also the payload which it finds, but it prepends the payload with the information about the signal, the mode which was used to actually receive this device, and all the information which is in the 04 command, but it also includes the actual payload. This can be useful, for example, when your devices are not really the actual meters, but they are just radio converters, and they contain in the payload the serial number of the actual meter, and you need to pair the converter with the meter to actually know what device to read out and to put into the list of devices to read out. Yeah, so this is something special we are showing here as well. And then at the end, we are showing how to trigger a scheduled readout, which is the 0B command. So we send it down, and the device starts sending the data from meters it captures, and then at the end it sends a report, and that's it. Okay, so, and then I will explain later a fragmentation layer. It is not shown in this diagram, but because LoRaWAN has limited payload size, you can send over, and some wireless and bus meters can have payload simply up to 255 bytes. There must be a fragmentation protocol which will fragment the uplink data into several frames. Okay, so let's show the actual consoles. I will first source my environment, and now I will launch main.py. Okay, and we are waiting for any received data. I'll click the button now. Okay, so we received now we send the configuration, which is dumped here. We send the ID of meters to read out, and we received here checksum of the IDs. You could see it here is the F6. And now I'm going to click this button again to make it faster so that it sends again a beacon. So this is the configuration part. Actually, it was quite fast. And now, because the serial line is connected, the device is waiting whether I want to connect or not to the device with the GUI.acrios.com, but not in this case. So I send there the request for scanning, and it is 2 minutes in TC mode. So you can see here it switched to it's called T1, but it's actually also receiving the C mode. And it is already capturing some IDs at RSSI. The logic here is that it adds in in the list only the ID if it was not received before, and if it was received before with a bad RSSI, it uses the best RSSI it can capture. If this logic is then used with our wireless and bus backend, what we do is we allocate the meters to the converters based on this signal, and because everybody reports the best value it can capture, we can then allocate the best we can the meters to the converters so that the probability of reception is maximized. In practice, it works quite well. Okay, so the scan should take about 2 minutes. You can skip or you can wait. Currently, I'm in my office, so everything that I capture here are meters I have for testing. I tried this close to where a lot of flats is, and it was, yeah, okay. So now you can see the data were reported, and here it was parsed and dumped in the console, and the device sent FB, which is end of scanning. We received end of scanning. We know it is the end of scanning, so we acknowledge on it, and the device enters sleep mode and will wait for 1 hour before it sends another beacon. Okay, so now the device is waiting for beacon, so I will again speed the thing up, and what we will do now is the payload scanning. So it will not contain only device type, ID, manufacturer ID, and RSSI, and the mode, but it will also contain the actual payload. And this time we will scan for 1 minute in Apator Metra proprietary protocol mode. So hopefully I have some devices here. I think I do. You can find the source code of this Python script and also of the Lua script running on the ACRIOS converter device in this text in the integration manual. So in case you would like to see what all these prints mean, it is defined in the code. But this is basically the scan table size of 800 is how many unique devices we will capture, and still we will do the logic that we only keep the entry if the signal is the best. When this is exceeded, this capacity of 800, everything is captured, and even if the ID repeats, it will be added to the list. But to be honest, if you are not really on a store with meters, it will not happen to you that you would capture more than 800 devices. So looks like I don't have any Metra device here. It's interesting. And some of them are also set up not to transmit all day. So maybe it's too late for them. They may be stopped at 6. So we were not lucky this time. There's FB, which tells us that it's end of the scan. We acknowledge that back, and now again we wait for a beacon to proceed further. Yeah, so this is how it looks like when you don't capture anything. It's nothing spectacular. What you would see is this thing. There would be just a print with hexadecimal string containing the payload. You must trust me. or check the code and run it yourself. Okay, so this time what we do, we send a scheduled readout with these parameters, and because I tell him not to defer the start, 0 meaning false, meaning start right now. It started the gathering process right now. So now it is trying to capture any of these devices which are on this list, and it will do so for several minutes. And if any of these devices is captured, then it is aggregated internally in the device, and once the size of the buffer is big enough, it is sent up to the LoRaWAN network server in this case. I will talk about the fragmentation layer. You can see that here already there is 0101 before the actual command byte or command byte. This is the actual fragmentation protocol which we have there, which helps us to split long commands into multiple fragments, which are then sent one by one. So the interframe timeout here is 10 minutes. So after 10 minutes of not receiving anything, it will actually stop. I will maybe use this time so that I can actually explain to you how this fragmentation algorithm works. So before the actual frame, there are 2 bytes. The first byte is meaning what is the total amount of fragments which will be sent to get the complete frame. And the second byte is simply the number of the fragment. So how this works is that when communicating from the device up, the device simply sends 0501, then 0502, 0503, up to 0505, and then it ends. That's as simple as that. And the remote party aggregates all these parts together, joins them, and then processes the whole payload, which can have, I don't know, 1000 bytes, which is impossible to send in one piece over LoRaWAN. When communicating back, it's a little bit more complicated because we are using class A, because we want to be low power. So what happens is that the device, when it receives as answer from the network server, for example 0501, it knows that it will receive another 4, it needs to receive another 4 fragments to get a full frame. So it will answer with 0001, which means 00 is like normally it would be the total number of fragments, but if it is 00, we can use it as a reserved value for answer, and 01 means I received fragment number 1 from you. And when the end device, when the ACR-CV, the converter, answers back, it opens an opportunity for the network server to send another fragment in RX1 or in RX2 LoRaWAN window. It will do so, and we either answer with 0002 and we continue like that, or if we don't receive anything down, because we must think of the thing like it is radio-based communication, so any radio frame can get lost anytime. So if nothing is received in 5 seconds, then the device will again send 0001 up, and the network server will know that the device didn't receive the second fragment and will repeat it. So it will again send 05, 02, and the rest of the payload. And like this with an iterative process, it will reach up to 0505, where the end device knows when it receives 0505 that this is the last fragment of the full frame. It joins all the parts together and then process them. This is not very efficient, of course, because you're sending messages back and forth, but it allows to send down the configuration of the IDs. We limit currently in our Lua logic the number of IDs to 240 wireless M-bus IDs. Every ID is 4 bytes. If you multiply it, it's, if I count well, 960 bytes, which you need to send down to the LoRaWAN device, which is approximately 20 messages which you need to send down. This typically happens only once when you provision the device with the list of IDs together, and then you don't need to do that, so it's okay to do it just several times during the lifetime of the device. Here I describe some details and facts. The maximum transmission unit which is used for the downlink is just 51 bytes because we don't know the data rate which would be used in the RX1 window, and in RX2 window in our case it's spreading factor 12. Here you can find an example log. In this example log, I was able to capture something even in the F mode. Yeah, here, single frame. So you don't need to trust me anymore. You can see I'm not lying. Here's the payload. If you take this payload and you go to, we can test it, and you go to backend wireless and bus ACRIOS.com, and maybe we go to backend, we go to test VPS, not this one, and you go to parser, Metra. Yeah, this parser is not available if you are not authenticated, but if we authenticate, then yeah, we got the value. Yeah, so this is the right payload you receive. And here I explained that the LoRaWAN script can use both LoRaWAN and NB-IoT. So you select here what interface to use. And yeah, I will go through the conclusion and then we can check what our device do. So you can notice that we use the same application level protocol as in case of wireless M-bus to NB-IoT, which theoretically allows us to integrate later with the backend I showed you. Currently, this integration is not done, but thanks to this design of LoRaWAN variant of our wireless M-bus to wireless M-bus converter, basically, it allows in future to integrate this with our backend. So, in case you are interested in this integration, do not hesitate to contact us. You can check our backend, and you can check also the wireless M-bus to NB-IoT article, which contains more information about the backend. Or you can write your own backend by implementing the same protocol or by getting inspired from this Python script. It's up to you. For proof of concept, I think it's always better to use what's available. Let's check this one. Okay, still receiving. It will be 10 minutes and didn't receive anything. So it looks like it's Friday, 7 p.m. Maybe the devices are already off. Most of the devices we encounter, or a lot of them at least, transmit from Monday to Friday, and they stop approximately at 6. So maybe this is not the best time to record this video, but we can always check the printout here, where I think I have captured something. Okay, I didn't either. So it's to motivate you to test it yourself. To test it yourself and see how it performs. So quite soon we should get timeout. If we actually receive something, the timeout will be in another 10 minutes. So I hope we will not receive anything, and we will receive the final report, which will tell that nothing was received. Yeah, interframe timeout, and this is the final report, and scenario finished, and 08 for confirmation of that, and the device goes to sleep. Okay, so that's it from me. Thank you for watching. I have shown you today how you can use our wireless and bus converter also with LoRaWAN, not just Narrowband IoT. In case you are interested in that, feel free to contact us. We can help you to integrate your network server, or at least to help you with some hints. And of course, you can use main.py script, which is available here, and do the integration yourself if you are interested. So thank you for watching again, and goodbye.